Today we're going to continue our investigation of shortcuts for taking derivatives. Yesterday's video we found out if two functions were added together or subtracted together, we could take the derivative of the individual functions. In other words, we found out that if we want to take the derivative of f of x plus or minus g of x, the derivative of that would be f prime of x plus or minus g prime of x. Just take the derivatives of the two parts. And I mentioned at the time that this does not work with multiplication or division. With multiplication and division, the rule is a little bit more involved, and that's what we're going to look at today, how we have two functions that are multiplied and take that derivative, and how we have two functions that are divided and take that derivative. So, first, let's take a look at this thing called the product rule. The product rule says if we have some function f of x that is a product of two different functions, let's say u of x times v of x, two things multiplied together that both have x's inside them. Well, the way we're going to take the derivative is we will take u prime of x, the derivative of the first, times the second function, plus the derivative of the second function, v prime of x, times the first function. In other words, it is the derivative of the first times the second plus the derivative of the second times the first. So let's take a look at some examples of some problems and how we can find those derivatives. So for example, if we've got some function h of x is equal to 2x plus 3 times 3x squared. Notice we've got two things here that are multiplied together. The 2x plus 3 is one, and the 3x squared is the other piece, multiplied together. So what we're going to do is we're going to use this formula in order to take the derivative. So h prime, the derivative, is equal to, we take the derivative of the first, in yellow, the derivative of 2x plus 3 is 2, times the second function, 3x squared, plus we take the derivative of the second function, in blue, which when we bring the 2 out front, 3 times 2 is 6x to the first, times the first function, which is 2x plus 3. So we took the derivative of the first times the second, plus the derivative of the second times the first. Clean it up a little bit with a bit of algebra. 2 times 3 is 6x squared, plus, distributing the 6x, 12x squared plus 18x. Combine like terms. The x squared gives us 18x squared plus 18x. And this is our derivative of the product. Let's try a little bit more of an involved function. See if we can apply the same principle to it. Let's say y is equal to the square root of x plus 2 times 3x squared minus 7x. Notice again we've got two things multiplied together. Square root of x plus 2 is multiplied by 3x squared plus 7x. So when we take the derivative, when we find dy dx, we take the derivative of the first part. Remember, the square root of x is equal to x to the 1/2. So we bring the 1/2 out front times x to the negative 1/2. The derivative of 2 is a constant, so that's the derivative of the yellow times the second part, which is 3x squared minus 7x. Plus, we take the derivative of the second part. The derivative of 3x squared, bring the 2 out front, we have 6x to the first, minus the derivative of 7x is just 7, times the first part, which is the square root of x plus 2. We could simplify this if we wanted to by distributing through parentheses, FOILing out, combining like terms. But we're going to be okay with this one because there's not much we're going to be able to do, and it's going to get pretty ugly. Let's do another example. How about we do y equals 3x minus 1 squared. Now, is this one really a product? Think about it. Squared means really we are multiplying 3x minus 1 times itself, 3x minus 1. So we do have a product. We have something multiplied by something. So when we take our derivative, dy dx, we can think about this as we use our product rule. We take the derivative of the first, which is 3, times the second, in blue, is 3x minus 1, plus the derivative of the second one. And the derivative of the second one in blue is 3, times the first one, which is 3x minus 1. And then we can simplify from here. Distribute the 3 to get 9x minus 3. Distribute the other 3 to get 9x minus 3. Combine like terms to get 18x minus 6. And we now have our derivative. So that's the product rule. The product rule is the derivative of the first times the second plus the derivative of the second times the first. What happens if we are dividing, though? Dividing two functions. When we are dividing two functions, we have what is called the quotient rule. And here we have f of x is equal to some function, maybe u of x, divided by another function, maybe v of x. So it's a fraction, but there's x's on the numerator, x's in the denominator. To kind of talk about this, we're going to say, I'm going to talk about the high one, that's the one on top, and the low one, that's the one on the bottom. So when I say f prime, the derivative of x, is equal to the low function v of x times the derivative of the high function u prime of x minus the high function u of x times the derivative of the low function v prime of x. And then we're going to divide the entire thing by v of x, the low. We're going to square the bottom, squared. This is probably the most involved formula of this unit. But if you think about a nice little jingle, it's not too hard to remember. Here's what I think about every time I take the derivative of a quotient. I'm going to do low d high. The bottom times the derivative of the top minus high d low. The top times the derivative of the bottom. square the bottom, and away we go. Away we go, because there's going to be a lot of algebra afterwards. Low d high minus high d low, square the bottom, and away we go. If you can just remember, low d high minus high d low, square the bottom, and away we go, you've got the hardest formula in the book memorized. So let's try a few. Low d highs minus high d low, square the bottom, and away we go. If f of x is equal to the simple fraction 3x plus 4 over 2x minus 1, you see the two functions. The 3x plus 4 is divided by the 2x minus 1. And so when we want to take the derivative with respect to x of f of x, we do low d high minus high d low, square the bottom, and away we go. So the low is 2x minus 1. D high, the derivative of the top, we should know is 3. Minus high, the top is 3x plus 4. D low, the derivative of the bottom is 2. All over, square the bottom, and away we go. The bottom is 2x minus 1. We're going to square it. That's our derivative. Low d high minus high d low, square the bottom, and away we go. Cleaning it up with a little distributing through the parentheses. Don't forget about the negative here. We're going to treat that like a negative 2 coming through. So distribute the 3 through, we get 6x minus 3 minus, treating it like a negative 2, negative 6x minus 8. Biggest mistake people are going to make is they're not going to distribute that as a negative. Be careful there. It's going to be a negative distributing through. All over, when we square 2x minus 1, we get 4x squared minus 4x plus 1. Combine like terms on the top. We've got negative 11, the 6 x's subtract out, over 4x squared minus 4x plus 1. And we've got our derivative. Let's try another quotient rule. Number 2, we're going to do f of x is equal to the function x squared plus 7x minus 2 all over the square root of x minus 1. Again, we notice two functions. X squared plus 7x minus 2 is divided by the square root of x minus 1. And we should be really good by now at recognizing that the square root of x is equal to x to the 1/2. And that way, we can pull the 1/2 out front and say the derivative is 1/2 x to the negative 1/2. So f prime is equal to low, the square root of x minus 1. D high, the derivative of the top, we should be able to see is 2x plus 7, minus high, x squared plus 7x minus 2. D low, the derivative of the square root of x is 1/2 times x to the negative 1/2. All over the low squared, square root of x minus 1 squared. This one we're going to say is done here because it's going to get pretty ugly if we simplify with that fraction and the square roots. So it's going to be ugly getting like terms to combine, so we're going to stop here. If there were no square roots, though, and there were no fractions inside of fractions, we would simplify it out, but we can be content with this. I want to do one last quotient rule problem, but this one we're going to make a little more exciting because we're going to combine the quotient rule with the product rule. We're going to see all these pieces together. So y is equal to 3x squared plus 1 times 2x minus 1 all over 5x plus 4. So again, you're going to notice we've got two parts that are divided. We've got a numerator divided by a denominator. However, inside that numerator, you'll notice there's a product multiplied together. So this is going to start to stack up the rules on us as we do this. So let's see if we can use both the product rule and the quotient rule in this problem. So, dy dx is equal to low. The low is 5x plus 4. D high, the derivative of the top. Now the top is a product. So in square brackets, to keep it all together, the top is the derivative of the first, 6x, times the second, 2x minus 1, plus the derivative of the second, which is 2, times the first, which is 3x squared plus 1. Notice inside those square brackets was just the product rule as we took the derivative of that product. Low, d high. Minus high. Well, the high is 3x squared plus 1 times 2x minus 1. D low, the derivative of the denominator is 5. All over, square the bottom, 5x plus 4 squared, and away we go. This one I'm going to say we can simplify out. It's going to be several steps. It's not going to be quick, but it's not hard either. Inside the parentheses first, we're going to distribute through. So we have dy dx equals 5x plus 4 times 12x squared minus 6x plus 6x squared plus 2 minus, I'm going to put the 5 out front and FOIL out these guys here. So that's going to give us 6x cubed minus 3x squared plus 2x minus 1 all over. We can go ahead and square the bottom, which is 25x squared plus 40x plus 16. Now let's go ahead and multiply out what's left. Oh, how about this? I'm going to combine these like terms here. 12x squared and 6x squared. That's going to save us a bit of work later. So dy dx is equal to 5x plus 4 times 18x squared minus 6x plus 2 minus 5 times 6x cubed minus 3x squared plus 2x minus 1 all over 25x squared plus 40x plus 16. Okay, we're almost done making it ugly so we can start simplifying. We're going to multiply out the 5x times everything, the 4 times everything, so we get dy dx is equal to 5 times 18 is 90x cubed minus 30x squared plus 10x. Distributing the 4 through, we get 4 times 18 is 72x squared minus 24x plus 8. Distribute the negative 5 through, we get negative 30x cubed plus 15x squared minus 10x plus 5 all over that denominator of 25x squared plus 40x plus 16. And finally, we're ready to simplify by combining like terms. We've got x cubes, 90 dy dx equals 90 minus 30 is 60x cubed. X squareds, we have negative 30 plus 72 plus 15, which is 57x squared. We've got a 10x minus 24x minus 10x is minus 24x. And then finally an 8 plus 5 is 13 over the denominator 25x squared plus 40x plus 16. We have successfully used the quotient rule and the product rule together to get our final answer. I want to notice in this problem along the way, it got ugly, but just because it got ugly and took up a lot of paper didn't make it hard. This was very, very basic algebra. All we did was distribute, combine like terms, multiply out and FOIL. Nothing we did not do in Math 95. We just are doing a lot more of it. So these are the two formulas that you should know for today. First, the product rule. The derivative of the first times the second plus the derivative of the second times the first. The second one, the quotient rule. Low d high minus high d low, square the bottom, and away we go. It's going to make for a lot of algebra to simplify. Not hard algebra, just a lot of algebra. Knowing how to do something like a quotient rule, though, does open up the opportunity for us to look at this application in business called a marginal average cost, which is the average cost per item for one more item. We already looked at marginal cost, which was the average cost to produce one more item. But really, if you think about it, producing one more item, that cost can be absorbed by some of the others. So how is the average cost per unit changing? Not just what's happening to the total cost, but what's happening to the average cost per unit. Because that's going to reveal to us how much more or less we're going to make on the sale of each unit. So average cost per item. And we can kind of figure this out intuitively. If C of x is the cost for x items, the way we calculate the average, we know from past experience that the average is the total cost divided by the total number of items. So we're going to make this new function, we're going to call it C bar of x to represent the average cost, is the total cost of all of the items, which we know is C of x, and divided by the number of items, which is x. Now, sometimes it would be easier, instead of dividing by x, we'll multiply by the reciprocal. So you'll also see C of x times 1 over x. Because the cost per item, the cost function often has fractions in it. And so if there's fractions in it, it's easier to multiply by a fraction than divide. And just like we expected from our past experience with marginal cost, marginal revenue, marginal profit, to find the marginal average cost, we take the derivative. So it's going to be C bar prime of x. The derivative gives us the marginal. How much more are we going to increase or decrease to get one more? Now, often we want to find out what's the minimum of this going to be. The minimum average cost. In other words, we want to make it cost as little as possible on average for each item. Well, it turns out, and we're going to look at this a lot more detail in Unit C, but it turns out the minimum average cost occurs when C prime of x, the derivative of the average, is equal to 0. In other words, increasing by 1 is going to have no effect on the average. It's not going to change. This is where the minimum average cost is going to occur. So, for example, if the cost to make X computers is C of x equals 4x squared plus 120 over 5x plus 1, we can find the minimum average cost. Well, first we need to find the actual average cost. This is the total cost, the cost to make X computers. And remember, the way we get the minimum, or the way we get the average cost, is we multiply by 1 over X, or we divide by X. So that's what we're going to do here, is the cost, C of x times 1 over x, is equal to the 4x squared plus 120 over 5x plus 1 times 1 over x. And that's going to be the C bar of x. So C bar of x, the average cost, if we distribute that x through the denominator, is 4x squared plus 120 over 5x squared plus x. We also know that the marginal average cost is the derivative of the average cost. So C bar prime of x, the derivative of this, notice it's a quotient, low, 5x squared plus x, d high, 8x is the derivative of the top, minus high, 4x squared plus 120, d low, the derivative of the bottom is 10x plus 1, all over square the bottom, 5x squared plus x squared, and away we go with now all of the algebra. So C bar prime of x is equal to, distributing the 8x through, is 40x squared plus 40x cubed plus 8x squared. Don't forget about the negative as we multiply this last part. It's going to be the most common error everybody makes. We're going to need to change the sign on everything as we FOIL. We need to take the opposite. So when we start FOILing, 4x squared times 10x, that's going to be negative 40x cubed 4x squared times 1 is 4x squared, so negative 4x squared, plus 120 times 10 is 1200x, plus 120 all over 5x squared plus, let's go ahead and multiply it out, why not? 25x to the 4th plus 10x cubed plus x squared. Combining like terms, c prime of x is equal to 40x cubed minus 40x cubed, that's 0. 8x squared minus 4x squared. 8 minus 4 is 4x squared, and then we've got plus 1200x plus 120 all over 25x to the 4th plus 10x cubed plus x squared. Oops, I messed up. I forgot to distribute that negative. I'm making a big deal about distributing the negative, and I missed it here and here. Backing up, that's bad. Negative, negative. So we've got minus 1200x minus 120. Don't forget that negative. Negative, negative, negative. Don't forget that negative. Okay, so now we've got the function here for the marginal average cost. But we want to minimize this. And the way we can minimize an average cost is we make it equal to 0. The nice part about a fraction is if we multiply both sides by the denominator, when one side is equal to 0, divides it out of the left side, and the right side, 0 times anything is 0, so we really have 4x squared minus 1200x minus 120 equals 0. And then we can try and start factoring. GCF first, always 4 times x squared minus 300x minus 30 equals 0. And I think we're going to have to use the quadratic formula on this. I don't think it's going to factor. And so we remember the quadratic formula, x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Notice as I'm doing this, I'm not using the 4 out front. We factored that out. It's not there anymore. Don't use that 4 out front. We got a negative times a negative inside, which makes a positive. So inside the parentheses, 300 squared plus 4 times 1 times 30 is huge. So x is equal to 300 plus or minus the square root of 90120 over 2. So we get 300 plus or minus, if we do that on our calculator, the square root of 90120 is 300.12 over 2. So that's going to give us, when we add 600.12 over 2, when we subtract 0.12 over 2, dividing by 2, we get 300.06 or 0.06. So the minimum average cost occurs at either about 300 items or 0 items. Okay, we're probably not interested as a company in making 0 items or 0.06 items. So we're going to say, as a company, we want to shoot to make an average of 300 items. When we make 300 items, our average cost per item is as low as it possibly can be. That is how we find the minimum average cost. Homework assignment today, you get to look at a lot of product rule and quotient rules. These take some practice, especially the algebra to simplify. Practice, practice, practice. And there might be an average cost problem or two. Take a look at them. Come to class with questions. We will see you then.